Professor Kai?
Yes, I'm here.
Yes, yeah. Okay.
Hi, long time no see.
Yes, long time no see. How is everything?
I'm fine.
Can
Hi.
you share the your screen?
Oh, yes. Okay. Sorry, I totally forgot to share my screen. Yes, it's over. I think it's over here. Okay.
Okay.
Can you see my PowerPoint now?
Yeah, I can see.
Okay, great.
Yeah. Okay. Slightly long title.
Yes. Yes.
Yeah.
Okay. But it's okay. It's just you know, it's some stories about the primordial black hole and the gravitational.
I see.
People love it.
Maybe this second section is for the gravitational wave.
Right. I was checking the talks, and I saw some of my collaborators, my colleagues are also in the meeting. It's really nice. So then I can give my time, just in case if they are, you know, if they are there in I mean APCTP, then they can help me to explain some details.
I see. Okay.
So we will begin at 11. Sorry, yeah, 11 local time. Good, perfect. Yeah, I wish I could make it to go there, but currently I can't. It's very pity.
Okay, let me start the second session in the morning of this workshop. And the first speaker is Professor Ifu Hai from University of Science and Technology of China. And the title of talk is Primordial Black Holes and Primordial Gravitational Waves arising from resonance in the very early universe. Okay, please.
Okay, thank you. Thank you very much. I was looking at friends in the meeting room at APCTP, and actually I'm missing there a lot because before the pandemic, I came to Korea to visit everybody year by year, but that has been more than 2 years ago. So, okay, so it is a really very great honor for me to join you guys in this exciting meeting. And I would like to take this chance to introduce some works that I've been working on, some nonlinear phenomenon of primordial fluctuations. And there are a bunch of collaborators in the related topic. And here I list most of the names, and some of my collaborators I noticed they have already participated in today's in this meeting as well. So okay, so the content of today's talk would be separated in the following. Actually, there are basically three stories. One is the so-called sound speed resonance mechanism that me and my collaborators just proposed 4 years ago. And then very recently, we realized this phenomenon can be extended to one line is to go for the early universe that can provide us a counterexample that violates the famous Lyth bond by introducing a resonant field during inflation. And the second is if we have this similar phenomenon for the gravitational wave sector, then it looks like we are able to utilize the gravitational wave astronomy to probe some potential new physics of modified gravity due to the sound speed resonance mechanism. So to begin with, everything has some kind of a starting point and some kind of the motivation. And the motivation for us to look at the nonlinear behavior of primordial perturbation is to ask you a question, under what kind of the condition we are able to produce the primordial black holes. And this topic has been very, very extensively discussed from many perspectives. And but I assume everybody here are the very good professional in this field. So to be brief, let me remind you, the primordial black holes is a hypothetical candidate for dark matter. And some people argue this can be used to explain the gravitational wave events that we have observed in the past a few years. Also, it is possible for primordial black hole to be the seed for supermassive black hole that we have observed in many galactic nuclei. And there are many other arguments. But if we really look at the theory over the primordial black hole formation, I mean, here I only review the simplest version, and basically it's to look at whether a local universe instability band, we usually characterize it using this the James radius, and to compare it with the Hubble radius, then we are able to derive under what time and what condition the black hole can form from the environment of the primordial fluctuations. And here we can give some kind of estimation. Say if we have the black hole formed in the primordial year, say around the electroweak scale, which is 10 to minus 10 seconds, after the Big Bang, then its typical mass is about 10 to 28 grams, something like that. And for example, if we really have some black hole formed at the same time of the neutrino decoupling, which is a half second after the Big Bang, then its mass can go up to 10 to 5 solar mass. And that can be used to explain some observational black holes, for example, the intermediate mass black holes. So then from the theoretical perspective, many attention have been paid to generate larger inhomogeneity in the primordial year of our universe, because only in that case we are able to make a black hole form over there, right? So then immediately there are many proposals, and here I'm unable to name all of them. So here I just pick up a few examples which are quite representative. For example, there's such so-called running mass inflation, which requires the slope of the potential to change from tachyonic to be the regular. So then there is a very manifest the running of the spectral index. In that case, one can have generated a large inhomogeneity. And also there are many works on the inflection point inflation. That is to say, if you have a period of slow roll connected with this inflection point phase and then go back to the regular inflation phase, then in this kind of scenario, there is a manifest variation on the slow roll parameter epsilon. So then you can also generate the large inhomogeneity. And I guess maybe 2 days ago, there was a talk by Shipi, if he was there. Then his recent works have been worked on this generating the PBH in the curvature scenarios. So if you introduce multiple degrees of freedom, and you also have a more parameter space to generate large inhomogeneity. And I would like to also refer to a paper by Mr. Sasaki-san and his collaborators on this comprehensive review, which is referred over here. But from from my perspective, when I look at this this requirement, so we want to produce the large large amount of the primordial black hole, then you know, once you tune the slope of the inflation potential, or you let the variation of the slow parameter to be large enough, or you introduce some multiple degree freedom, it looks like this kind of scenario is a little bit artificial, and you need to do it like playing the toy like a baby, right? But what if we don't introduce much degree of freedom? We don't change the background evolution too much. Is it still possible for us to generate a large inhomogeneity in, for example, in single field inflation? Typically, this is almost impossible because there's some kind of the no-go theorem for the single field slow inflation, right? However, a lesson that we can learn from the cosmological perturbation theory is that the evolution of perturbation and the evolution of the background, actually, they are two independent stories, right? So for slow background, we usually need the epsilon and the eta, these two parameters. Basically, this is enough. But if we really want to full characterize to describe the cosmological perturbations, we still need to take into account the effect of the sound speed. So then what would happen if we have some non-trivial sound speed? Well, a lesson we already know for many years is that if we have the sound speed involved in the perturbation theory, then usually it will lead to some, for example, non-Gaussianity, primordial non-Gaussianity. And if this CS is too small, then such kind of the theoretical models could have already been ruled out by observations like the Planck constraints. So this wouldn't work very much. But then another possibility is that what if the sound speed is not that small? It's still around the unity, right? Then, but let's say we introduce a very small modulation to this sound speed. And this is parameterized as the equation in this red box. And you can see what we actually did was to assume CS is still around the unity equal to 1, but we introduced a very small modulation. The amplitude is characterized by this Kasi parameter, which is small. Usually it has to be small. And then we introduce a short period, not short, a period of the oscillation here with frequency, denoted by this K star, this due to some unknown reason, okay? And then we rewrite the, here I write this equation motions for the perturbation using the standard Mahanov-Sasaki variable. And then you are able to introduce, you can rescale this perturbation equation in terms of the Massieu equation as described as below, which is shown in the bottom of this slide. I don't know if you guys can see my mouse, but so then I can only describe it in this way. But then once you can, if you can obtain this Massieu equation, then you can immediately realize it might suffer from the instability. But this instability band is very narrow, so this can be referred as the narrow resonance. So for the narrow resonance, usually it does not modify the background much because the back reaction is totally under control. However, it can significantly modify the profile of the primordial perturbations. So then let us take a look at what would happen to the Hall spectrum.
Question. Yeah,
yes.
Yeah. Previous page.
Sorry.
Previous page.
Yeah. Okay. Yeah. This is the slide.
Right. So, is there some specific model to give this variance CF? So, did you consider this assume this? Yeah.
Okay. Yeah. Actually, later on, I will introduce one specific model.
Okay.
Yeah. Okay.
Thank you.
Good. Thank you. Okay. Following what I mentioned previously, this narrowness, it won't change the background. However, it will change the Hall spectrum on its profile. So then, well, after not that lengthy calculation, to be honest, the calculation is quite simple. Then you can see by looking at how to say this almost this single equation. This is the expression for the Hall spectrum P zeta, and the first term, this AS times P over KP NS minus 1. Well, everyone knows this is the standard Planck convention for the primordial Hall spectrum, right? AS is the amplitude of the Hall spectrum, NS is the spectral index, and the KP is the pivot scale. So that is standard. Everybody is happy. However, due to the narrowness that can be induced by this oscillating sound speed, we can get a lot of the peaks, some spiky enhancement on the Hall spectrum, which can be described effectively by this a sum of this infinite delta function. And before all these delta functions, there is a common factor. You can see it's equal to C P star times e to minus C P star tau I. This exponential term, well, there's a minus, but actually in inflation, tau I is negative. So this one is the enhancement factor, exponential enhancement factor. And then we can numerically solve the same system. And then below the left panel of this slide, you can see the Hall spectrum looks like is described by this purple solid curve. It can safely satisfy the Planck constraint, and it can safely satisfy the constraints from the large scale LSS, the large scale structure observation, as well as the mini halo constraints. And eventually by choosing appropriate parameter, then there are many peaks that appeared in the small scale. So then that can be used to produce the primordial black hole, which typically is described by this FPBH parameter. This is the mass fraction of a primordial black hole. So then we can translate this scenario to the plot shown in, the right figure shown in this slide. And by looking at this scenario, a question that follows is since it changes the primordial density perturbations, so then what would happen to the gravitational wave, right? So actually, that's a very important question. The interesting thing is, usually when we look, this slide shows the evolution of the one fixed co-moving Fourier mode evolving from the beginning of inflation and then until the end, until the radiation domination. And you can see for each Fourier mode, it starts evolution at a sub-Hubble scale and evolve to sub-Hubble scale, get frozen, decoherent from the quantum fluctuation to classical perturbation. And then evolve back to the Hubble horizon to form the LSS. And usually we say if we have a primordial black hole formed, that is the moment is referred to the radiation domination. And basically there's no drama before that. However, if we really look at the evolution of the gravitational wave, since the resonance itself has already began during inflation, then we should consider taking into account the contribution of this effect starting from the inflation phase. So what we did in the following is that we calculate the induced gravitational wave starting from the inflationary stage by taking into account two contributions. One part is the integral from the super-Hubble regime, and one part is from the sub-Hubble regime. And you can see this super-Hubble contribution is many order of magnitude lower than the sub-Hubble contribution. That actually is in agreement with most of the the literature works, and because that is why when people look at the induced gravitational wave from that also form the primordial black hole, they only consider the contribution during radiation, because the contribution at the super scale is totally negligible. However, since, as I mentioned, the resonance itself is a nonlinear process and it has already begun during inflation, then the Hubble contribution could be very significant. That can be described by this red curve. So then we sum all these contributions together, which can be shown in the bottom of the bottom plot of this slide. And you can see the red curve refers to the contribution during inflation, and the blue curve refers to the contribution from the radiation phase. And you can see these two actually forms kind of the double peak spectrum. And well, actually here I refer to some pioneer work that kind of teach us how to do the calculation. And here there are some references over here. But for us, in our work, what we observed, this kind of the two-peak spectrum generally is a multi-peak gravitational wave energy spectrum, which is very rare in many theoretical models. So while another question follows that since we introduced this sound speed for the primordial density perturbation, which only involves the inflating field, but what if we have in general, we always have a multiple degree freedom. And what if this, is this phenomenon robust in single degree freedom or multi-degree freedom? So then we also extend this work by including curved field as well. And in this case, we are taking an extreme case that we assume the inflaton is just a regular, but only the curved experience the sound speed resonance by introducing a non-trivial sound speed parameter. And again, you can see there is a significant enhancement over here. But the difference is that the sound speed resonance can enhance the curved fluctuation, but it can only be imprinted on the pulse spectrum of a curvature perturbation by enhancing the transfer coefficient. This transfer coefficient is described by this lambda parameter here. So you can see this enhancement is a little bit more smooth. And then it comes back to the question, how to realize the SSR, the sound speed resonance in inflation. And in fact, there are there are quite many approaches. And here I kind of only list two lines. One is directly construct this sound speed resonance by virtue of the Dirac-Born infinite inflation model. And the other line is by abandoning the specific model, but starting from the effective field theory and try to find the operators that can induce this oscillating CS square. And the first let us take a look at the realization in this DBI model. For DBI model, we know C square actually can be exactly, there's the exact formula. This C square equals to 1 minus F phi dot square. This F is the warp factor as described by this first line of this slide. And then we can write down the equation of motion. And usually for DBI models, the evolution is still dominated by this potential, but just the phi and phi dot could be large. So what we really did to realize this scenario is to make the following perturbative approach. We separate the CS square to be two phases. One is the non-oscillating phase, that is the regular DBI model. Then for the oscillating phase, we introduce a small deviation into this warp factor, which is described by this delta phi function. And as I mentioned, we consider the background evolution is insensitive to the perturbation itself. So then the background evolution is the same as the regular DBI inflation. And then we can write down the dynamics of the inflated field using the Hamiltonian Jacobi formula. And then we can proceed to reconstruct evolution of the Hubble parameter as a function of phi, as well as the V phi, the potential as well. And since we have already introduced this oscillating sound speed, then in this case, we are able to reconstruct the warp factor. That is, we reconstruct the delta function, delta phi potential form. And then the warp factor form actually is given in this slide as well. You can see there's a cosine function. Inside the cosine function, there is the exponential form. Okay, so previously I give you this specific example. And the second case is to look at the effect from the viewpoint of effective field theory. We argue this resonance actually is can be realized by introducing multiple degree of freedom. But if we are able to integrate out the 1 degree of freedom and only leave this single degree of freedom, then it should be the same as the SSR. So then we go back to the multifield dynamics. By looking at the multifield case during inflation and see if the resonance can happen, the motivation is kind of in analog of the reheating or preheating. And we know for the preheating, the energy stored by inflated field is able to be released effectively by introducing a second field, right? So what will happen during inflation? So what we we take the we are kind of extend the scenario from two models. One is the axial monodromy inflation, because for axial monodromy inflation, there indeed exists the cosine modulation along the potential. And then since we introduce a second field, the second field, we take this model in analog of the relaxation scenario. So it's just a linear function of the phi field. So to combine these two together, you can see we also make a plot of this potential in this 3D scenario. Then you can see this bright and dark area refers to the oscillations along the potential. And the inflating field initially evolve along the phi field and then experience the modulations. And then it will lose the kinetic energy and eventually locked somewhere, some valley, and then rolling down along the valley, to this chi field direction. And then we can write down the field equations. This is just a straightforward expression. And you can see the delta chi field can be sourced by the delta phi field. And this delta phi field, if you look at it carefully, this is the second equation of this perturbation equation. its form actually is very similar to the Maxwell equation. So then again, there exists the narrow resonance that are happening to that phi. And eventually, when we carry out the power spectrum, this is the numerical result, we find its profile is exactly the same as the previous one. And then it means we can realize this narrow resonance during inflation, and the result is pretty much similar to the sound speed resonance as well. But then another question that follows is, which is also a very interesting question, is it possible to realize such kind of the resonance in the same B window? Well, this is very challenging, you know, because usually people don't like the resonance in the same B window because we already have the WMAP, Planck, BICEP, and many other same B observations that put very strong constraints on the primordial perturbations. Why we consider such kind of, how to say, stupid question, okay? Very stupid question. Okay, so let us go back a little bit, the inflation perturbation theory. For inflationary perturbation theory, I mean, here I refer to Daniel Bowman's the review article, go back to 2009. And if you see the density perturbation evolving from the subhorizon and evolve to superhorizon, it gets frozen and it's conserved, and then go back to subhorizon to form the LSS and leave the imprint on the CMB temperature and the enthalpy, right? So that means during inflation, there are two power spectrums that for theoretical cosmologists are most concerned over. One is the dimensionless power spectrum for the curvature perturbation, and that is given here. Again, this PR equals h square times h over phi dot square, and the h actually is exactly the field fluctuation in the de Sitter background, and the second term h over phi dot actually is a kind of the reverse of the square root of a slow roll parameter, and that describes how the field fluctuation is converted into the curvature perturbation, right? And then this, of course, has been exactly measured and in extremely high precision in the CMB window, which is beautiful. And the second power spectrum that we're really concerned over is the power spectrum of primordial gravitational wave. And according to the theoretical calculation, the gravitational wave has nothing to do to the curvature part, at a linear order. Then this power spectrum should be equal to h square, modulated by some order 1 parameter. And that is exactly the vacuum fluctuation in the de Sitter background. And in this case, if we want to probe the primordial gravitational wave, we have to go give hope to the CMB window as well, because the CMB window, except for the temperature and enthalpy, it still encodes the information of the polarization. And so far, we already have the T, the temperature and enthalpy, and we have the information of the E mode polarization, but we don't really know that much about the B mode. We actually know some information like the lengthening B mode, B mode contribution. We have a little bit knowledge about the contamination from the foreground, but we still haven't yet figured out the primordial B mode signals. So this is why, go back to the previous question, if we have the resonance effect, is it possible that we don't change the power spectrum of the curvature perturbation, but we could enhance the signal of the primordial gravitational waves? And if this could happen, then it can give the experimentist, the cosmology in the experiment site, a huge motivation for them to look for the primordial B mode. So this is why we raise this question. Well, to begin with, then somehow it's got a sad news is, a sad and old news is that there exists such a famous Lyth bond from the lesson of the effective field theory. The Lyth bound actually can provide a theoretical interpretation of the tensor to scalar ratio. The tensor to scalar ratio is the Hall spectrum of the tensor mode over the scalar mode. And it actually describes the variation of the field during the inflation. And usually if we limit ourselves with the E40 number as a 60 eFols, then this is a limited inflationary period. And then we know the if we have a large field excursion, then tensor to scalar ratio has to be larger than say 0.01, right? But currently the observational, from the observational side, we already know the upper limit on tensor to scalar ratio is smaller than 0.036. So that means, in fact, there's no big space for us to let the field excursion to be large enough. And also from the theoretical perspective, if we really have the field excursion to be longer than the Planck distance, the Planckian distance, then usually we will be troubled by some high order quantum corrections. That is the famous eta problem, go back to 1990. So then, okay, here the following is what we did last year. So we say, okay, can we find the counterexample to violate the Lyth bound? And still we enhance the primordial gravitational wave. But this enhancement can only happen to the narrow regime. Then what we actually did is to, following the previous model, like the two field model, and the one field is almost massless, and it only contributes to the controls the curvature perturbation. And the other field is very massive. It's comparable with H in most of the time. So it doesn't contribute to the curvature perturbation, but it still can experience the resonance and coupled to delta chi only gravitationally. So the contribution to so it plays a role of the ice-curvature perturbation. And here from the effective field theory action, which we write over here as S3, then we can read three conditions so that we are able to realize this counterexample. The first condition is that the resonance must happen inside the Hubble radius. I mean, of course, so in this case, we can get the narrow resonance, right? And the second condition is that the random heavy field must decay out at the super Hubble scale, because we don't want to change the curvature perturbation. So then it put a theoretical constraint on the effective mass. And the third condition is the resonance field mass need to be small enough, just right after the Hubble crossing, and so that we can have we don't expect the gravitational wave also decay out. So then I'm not going to the details of the model construction, but only show you the model is over here, and we numerically calculate the evolution of a chi field and the phi field that can sustain more than 60 E40 numbers. And you can see the variation of the both fields are much less than M Planck, right? It's just almost 10 to a -2 order of Planck distance. And even for this kind of a scenario with a very small field excursion, we still can induce the, we don't change the curvature perturbation, but enhance the gravitational wave significantly. And then we translate this enhancement of the primordial gravitational wave into the CLBB, that is the primordial B-mode signal, which is described by, we choose two group of the parameters. And one is this, one is a red curve, and one is this black curve. And you can see, well, we also confront with, one is to confront with the Lansing B-mode signal, and one is to confront with the light bird sensitivity. And you can see even much below than the upper limit provided by current observation, we still have the chance to produce the observable signal for the primordial gravitational wave that could experience the resonance during inflation, which is displayed in the right panel of this slide. And you can see there's a cross of the red and black curve crossing over the light world sensitivity at a small error regime. So this is very exciting because this, from the theoretical level, we provide the experimentist with a very solid, very concrete observational object. Okay, I guess I still have maybe 10 minutes. So I'm trying to share with you a very short story, which is, well, previously we are talking about the early universe, but what will happen for like this SSR can happen here in the past history of the cosmic expansion. Say, what if there is the sound speed resonance happening to the gravitational wave propagating speed? But then, well, there are two lessons. One is from the particle physics. We know go up to from the gliders, go up to 13 TeV. There's no signal for new physics for particles. Okay, no drama over there. Then we give the hope to look for the new physics in the gravity sector. And for gravity sector, we, thanks to the gravitational wave astronomy, especially from the how to say, the observation in 2017 for two neutron star merger that provides not only the gravitational wave, but also electromagnetic signals. And that yield a very tight constraints on the propagation speed of gravitational wave, which is almost equal to light speed. But fortunately, this observation happens for the event with a redshift less than 1. So we still can give the hope to something that might be even earlier or might be even more distant. And from the other side, we, along with the theoretical development of the gravity series in the past years, there are many developments like the Hondesky gravity is a very representative one. And that gives us a lesson. The speed of a gravitational wave is not necessarily equal to 1, but can be some very complicated formula. And also there are some arguments from so-called the Einstein-Gauss-Bonnet gravity, and that also yield the sound speed deviating from unity. So then and then I discussed with my colleagues, and the following question is, what if this deviation can yield a very short oscillating period for the gravitational wave speed? And of course, then we parameterize the propagation speed of gravitational wave described by this red box. And inside this red box, you can see the amplitude of the oscillation actually is decaying out along the time, so that at the late universe, Cg squared equals to 1, so that it recovers the light speed at in local universe. And then we see in this case, if we write down the equation of motion for the gravitational wave as well, then it looks like, and if we neglect the friction term, then this formula is again can be written in terms of the Massieu equation. So I'm going to skip this explanation of this resonance band, but just to remind you, in this case, the resonance band is even more narrow, because there's a competition of the friction term and the how to say, the instability band, the Massieu instability band, and then only when the perturbation mode scanning through this band can experience the enhancement. So I would like to only directly list the result here. And here what we did is to consider two examples. One is to assume if there's a new physics of the modified gravity at TeV scale, and this TeV scale can yield these oscillation terms, then it can generate a very sharp peak on the any spectrum of a stochastic gravitational wave background. And here we actually have already taken into account the signal to noise corrections. I mean the background noise as well. So you can see there's a lot of the spiky forms, but they are the noise. so you don't need to worry about that. But you can see this, and if this new physics for modified gravity appeared in TV scale, that the narrowness leading to a very sharp peak that reach the sensitivity of a Lyth experiment, which is about 10 to minus 2 hertz. And if there is a new physics that appeared, the operator appeared at a 10 to 4 TeV, which of course is a much higher than any collider any scale, then this peak can be moved to 100 hertz. That can be, comparable with LIGO, Virgo, and Cargo, and so on. So those ground-based gravitational wave detectors. So this is a very interesting result. Also, can connect our theoretical setup with the observation, so that we can test them in experiments. Okay, so I think I can give a very brief summary of what I have shown here. And as I mentioned, the primordial black hole, well, it's interesting because a lot of people discuss that. And then we want to produce a primordial gravitational wave in an efficient way. And then we propose this new mechanism, which is called the sound speed resonance. And well, we have worked a little bit on this mechanism. However, we believe there are a lot of underlying physics of SSR needs to be explored. And we discussed the gravitational wave induced by SSR. And we realized this is very different from any previous study, because in previous study that associated with the PBH formation, people only consider the induced gravitational wave in the radiation phase. However, for sound speed resonance, the nonlinear effect has already began during inflation. So the contribution of the sub-Hubble perturbation during inflation has also made a very crucial contribution to the NS spectrum. And then this indicates the gravitational waves induced from SSR can be a very promising probe to detect the physics of the early universe. And after that, we also raise a question: what if this in the nonlinear resonance can only affect the gravitational wave, but didn't modify the density perturbation during inflation? Then what would happen? Then a lesson that we learn is this can break the famous Lyth bound and can provide a very interesting, the observational object for CMB observation in the near future. And at the end, we end with another story that by arguing that the new physics of modified gravity might be able to be probed with the future gravitational wave, the forthcoming gravitational wave astronomy, because of the possible existence of a sound speed resonance happening to the gravitational waves. Okay, thank you very much. Thank you.
Thank you for interesting talk. Any question?
I have a question.
Yes, please.
Right. So regarding the modified gravity scenario, for
Yes.
oscillating speed of graviton, so is there any some specific model that you give that kind of oscillation?
You mean only for the gravitational wave, right?
Right. So
yes. In fact, okay. Yeah, this is a good question. Well, of course, here we did this parameterization. However, I would like to refer to this model. This model was studied by Glavin and Chunhan Lin. Go back to 2019 or even earlier. They actually this is what we discussed. I discussed with Lin, and he told me my parameterization here can be exactly fit in this form. You can see that's why we have this 1/tau square. because this is h square. So something like that. And the oscillation can always happen if you have the field. And that is exactly in this term. Yeah.
Okay. I have a nice.
Can I ask another question? So general question,
Yes,
question is that you consider some primordial black hole thing. So is there any, I mean, what about, I mean, the non-flat universe you consider? I mean, if you, so you consider only the flat universe, right? What about the
flat universe?
Yeah,
right.
yeah.
That is a good question. Right. I consider the flat case because it's the simplest one. I can calculate it. But
So
if if we consider the non-flat, first of all, I think for example, the open universe, it could be okay because there's no boundary condition issue. But this story might be interesting or complicated if we really look at the closed universe because then I can't answer you right now, but maybe I will think about that and we can keep in discussion later on by email.
Okay, thank you.
Thank you very much for your interesting question.
Okay, other question?
I have a very nice question. So if the sound speed changes, then is there any harmful effect to LIGO data analysis or totally irrelevant?
For example, here, I actually include the LIGO sensitivity curve here. At the current design, I think LIGO is difficult to yield the constraint on the gravitational wave speed in single way. However, if we really have more and more observations like the GW 1709, 18, right? I didn't remember the number. So once we have more and more neutron star merger that can yield both the gravitational wave and electromagnetic signals together, then I think this is really a very interesting question because I'm looking forward to the more data and this similar result. And you see, there will be some more and more constraints on the GW speed. Yeah, this is very interesting.
Okay, thank you.
Thank you very much.
I have one question.
Yes, please.
And you considered about the mass inhomogeneity in your SSR, is it?
Sorry, I didn't follow your
mass inhomogeneity. Mass inhomogeneity.
Mass.
A mass of scalar field.
Massive scalar field.
Mass,
yes.
mass itself of scalar field, right?
Scalar field.
Maybe in the first slide of your talk, I saw
this one.
No.
Okay. Oh, I think I know what you're talking about. This one, right?
Yeah. No. Previous one.
This one.
No. Here, learning mass inflation. Learning mass here is some kind of
running mass. Right.
time dependence of mass.
Running mass, I think it depends on the potential, right? I think it's somehow what can I say? Running mass, for one thing, it definitely is model dependent. For some of the running mass model, its mass actually is varying at a different cosmic time due to some reason. Yes.
That is the reason.
Yeah.
Okay. I see. Okay, now it's time. Okay. Let's thank speaker again.
Thank you very much. I really hope to come back to see you soon sometime. All right.